phase diagram that is both very simple and also completely impossible to calculate. And this is joint work with Ji Lee and Toby Cubitt. So computing phase diagrams is a pretty central program in physics, given that they chart the macroscopic behavior of a system in response to its microscopic interactions. And a classic example of this really is this transverse field Ising model Hamiltonian on the board, where the phase diagram can be exactly solved. And the setting is you've got spins on a 1D chain, and the Hamiltonian is describing this competition between spin-spin interactions between neighboring spins that favors that they both either point up or down, and then this external field which is favoring that it aligns along the x-axis. And by mapping this to a free fermion problem, it's well known that for small values of this external magnetic field, the average magnetization of the system is non-zero. It's in this ferromagnetic phase. And then for large values of the external magnetic field, this average magnetization is zero. And this is a very simple phase diagram. We know how to calculate rather more complicated phase diagrams. This Hamiltonian here describes electrons hopping on a 2D lattice in a perpendicular magnetic field. And the exact solution of this gives this phase diagram here, which is really very complicated. It's got this fractal structure, infinitely many phases. But I don't think anybody expects that we should be able to exactly solve for all phase diagrams. So there are a number of methods, a number of algorithms that you can apply to finite-sized systems and get the phase on the finite-sized system. And then the hope is just that you can extrapolate these results through to the thermodynamic limit. And we would really like to know if this is a valid approach. Will these algorithms, or really any algorithm that you could think up, always tell us something about the phase diagram in the thermodynamic limit? And this very nice paper from 2019 says no. Building on undecidability of the spectral gap results, they write down a Hamiltonian with a phase a one-parameter Hamiltonian with a phase diagram that is uncomputable as a function of that parameter. And uncomputable means that there's no algorithm running in finite time that when you give it this Hamiltonian as input, it returns the phase it's in. And the phase diagrams that you get out from these Hamiltonians that they've constructed look like on the board. That's one example. The brown is a gapless phase, the green is a gapped phase, and then the gray is some unevaluated parameter regime. And there are two phases, but they switch between each other infinitely many times. Not only is this a quantitatively very complicated phase diagram because it's uncomputable, it's also qualitatively really quite complicated. And this motivates the question of our work. Is this qualitative complicatedness necessary? Can we design a Hamiltonian with a phase diagram that looks just like this? There are two phases, there's a single transition between them, and yet it's somehow uncomputable. And this may seem a little too simple for uncomputability, but in fact, we're going to be looking to design a Hamiltonian such that it undergoes this phase transition exactly at an uncomputable number, and that's how it can be uncomputable. So what actually is an uncomputable number? Well, almost every real is an uncomputable number. If you draw a universe uniformly at random, with probability 1, you'll get an uncomputable number, but it's really not very easy to say what that number that you've got out actually is. It's not very easy to define an uncomputable number, even though there are so many. And one sort of uncommon example of one that you actually can define is this Chaitin constant here. So the Chaitin constant of a prefix-free, which is just a technical condition, Turing machine, is this omega here. It's a sum over bit strings such that the Turing machine halts on the bit strings. And whenever it does halt, you add this 1 over 2 to the power of the length of the bit string. And this prefix-free condition means that this sum converges to a number between 0 and 1. And so we can sort of think about this as the probability that this Turing machine will halt on a random input. And actually, because we're defining it with respect to a Turing machine, this isn't really a single number, it's a family of numbers. And it has some quite interesting properties. First of all, it's uncomputable. And maybe you can see this by, this is really just encoding the answer to the halting problem for this Turing machine on all possible inputs. And the halting problem is really the classic undecidable problem. So that's why it's uncomputable. And really there's something actually much stronger going on, which is that we could imagine being able to write down an uncomputable number such that you can compute infinitely many of the digits, and then infinitely many of them you can't. That's not what's going on here. This is stronger than that. Any set of axioms can compute only finitely many digits of this number. So yeah. It's also known that Chaitin's constant is algorithmically random. And there's a sort of interesting tension between uncomputability and randomness in that one implies lots of useful information and then one implies none. And as a result of this algorithmic randomness, it's known that this number is normal. So every sequence of n digits appears with probability 1 over 2 to the n. So the digits really do appear as though they've been generated just by flipping a coin. And yeah, so this number is a bit string where, of infinite length, where each digit is either 0 or 1. But rather surprisingly, we can choose a universal prefix-free Turing machine so that the standard axiomatization of mathematics, if arithmetically sound, cannot determine any bit of this number. So even though every digit is either 0 or 1, and we even know something about the statistical properties, which is that they all appear with equal probability, there's not a single bit that you could point to and tell me what it is. So for our setup on the Hamiltonian side, the Hamiltonians we'll be proving hardness result for are defined. They're a family of Hamiltonians H sub L, where it will be defined on an L by L 2D lattice. We're going to restrict to nearest neighbor interactions and a translationally invariant terms, finite local dimension, and bounded interaction strengths. And all of this is to say it's really a very simple form. And the simpler the form of the Hamiltonian that we can prove hardness results for, the better the hardness result. And so what our task is going to be is we're going to have to give these terms H site, H col, and H row, which are 1 and 2 body respectively. And then they get combined into a Hamiltonian as on the board with open boundary conditions. And the thermodynamic limit can be taken by taking the lattice size to infinity. And we're going to be talking about gapped and gapless phases as being as appearing in our phase diagram. And what I mean by that is for a gapped phase, there's a system size above which the spectral gap is always lower bounded by a constant that's greater than 0. And then in the gapless phase, there's a system size above which there's a region above the lowest energy that the spectrum of the Hamiltonian is dense in. And these aren't opposites of each other. There are systems like gapped systems with degenerate ground states that aren't either of those, but that doesn't really matter for our purposes. So the result. We can write down terms, H site, H col, and H row, such that the Hamiltonian, H sub lambda phi, given as so, has the phase diagram on the board in the thermodynamic limit. And slightly more formally, for any prefix-free Turing machine M, we can write down an integer d, a d by d matrix H, 3d squared by d squared matrices A, B, and C. Define our Hamiltonian as shown by setting the one-body term to be this matrix H, one of the two-body terms to be this matrix C, and then the other two-body term as shown on the board. And these matrices that we've written down are such that the matrix entries are all of the form x plus y over square root 2 for x and y integer. So they're a very simple form. Nothing strange is going on whereby we're putting in uncomputable numbers and then, oh no, we've got something uncomputable out. This is not that. They're going to have bounded interaction strength. And then the resulting phase diagram, for values of this external parameter mod1 that are less than Chaitin's constant, it's going to be the system's going to be gapless with a disordered and critical ground state in the thermodynamic limit. And we're going to be able to identify a local order parameter such that the expectation of this order parameter in all low energy states is 0. And then for phi mod 1 greater than or equal to Chaitin's constant, the system's going to be in a gaps phase with an ordered and product ground state in the thermodynamic limit. So again, this same order parameter is going for the unique ground state is going to give an expectation value of 1. So what exactly is this Hamiltonian that I've claimed we've constructed doing? So if you look at the phase diagram there, essentially what the Hamiltonian seems to be doing is asking itself, is phi less than Chaitin's constant? And then if the answer is yes, it's going to be in a gapless phase, and if the answer is no, it's going to be in a gap phase. And this really rather looks like a computation. Fortunately, it's quite well known how to embed computation into Hamiltonian ground states. For some computation made up of gates, it's quite easy to write down a Hamiltonian such that the ground state tracks the evolution of this computation. And by a very nice sequence of works, this Hamiltonian that you write down can actually be of a very simple form. It can be local, it can be one dimension, and it can be translationally invariant. So we can detail our picture of what the Hamiltonian is doing a little bit. We can start to talk about quantum Turing machines that we're then going to embed in the ground state of the Hamiltonian instead. So we're going to design a quantum Turing machine such that if phi is less than omega, then it halts, and then somehow map that to a gapless Hamiltonian. And in the other case, it loops, and then somehow map that to a gapped Hamiltonian. So first off, we can see that the way that we have access to this phase phi is it's a phase. So it's not really necessarily obvious how you say whether a phase is less than some number or not. How do you actually perform that comparison? And then as well, how do you do that when the number that you're comparing it to is an uncomputable number? You can't know it. So how do you compare another number to it? Fortunately, this first point is really a solved problem by previous work. You just do phase estimation to get the phase printed out onto the qubits or qubits. But the second point is specific to our work. And the key idea really is that although it's an uncomputable number, that doesn't mean you can't approximate it. You can approximate it from below by this sequence omega sub s that's monotonically increasing and equals Chaitin's constant in the limit. And I claim that this approximation omega s, which actually you can just see from these properties here, satisfies these completeness and soundness conditions. You know, if phi really is less than Chaitin's constant, then that's going to be reflected in its relation to the approximation at some point. And then the other way around, if it isn't less than it, then you're never going to find an approximation that it's less than. So what is this approximation? So just looking at the definition of Chaitin's constant again, and that it's the sum over bit strings that the Turing machine halts on, we can really just take this approximation to be the sum over bit strings that it halts on within s steps. And kind of interestingly, it's known that among all numbers that you can approximate from below, this approximation converges the slowest. But that doesn't matter. So again, detailing what the quantum Turing machine is doing a little bit more. First, it's performing phase estimation, so that it gets out an approximation to this external parameter. Then it's computing an approximation to Chaitin's constant, and then it's comparing the two, and either halting or looping. And if we pick our S cleverly as a function of system size, we can ensure that nothing goes wrong when we're considering these approximations rather than considering the actual values. So they satisfy these completeness and soundness conditions. So this left-hand side of our diagram is, morally, ignoring the details, now implementable. And as for how you actually map this to a gapped or a gapless Hamiltonian, fortunately the ideas from this are really present in this sequence of undecidability works. Just in brief, first off, you map the QTM to a Hamiltonian on a spin chain and add a penalty for looping, which opens up a nice ground state energy difference between the two cases. But unfortunately, this ground state energy difference vanishes in the thermodynamic limit. So we have to boost it, which we can do using something called a stretchy squares tiling. And then finally, you can convert this boosted difference to a difference in spectral gaps, which gives you your gapped and gapless result. So in summary, we have managed to write down a Hamiltonian such that the phase diagram is uncomputable, and yet we can really say rather a lot about it. And furthermore, it's got this uncomputable number attached to it, sort of describing its macroscopic properties, even though all the microscopic interactions are fully computable, which is quite interesting. And another sort of Hamiltonian phase diagram that maybe you would like to see is something similar with two gapped phases instead of one gapped and one gapless. This is an open question. Thank you.
So we have plenty of time for questions.
Thanks for your talk. Just a simple question. Do you consider looking for cosmograph complexity because it's also uncomputable kind of measure?
Yeah, I imagine you could also do it with that.
Thanks.
Thanks for the great talk. I have no idea, it's a naive question, but why would you care about, let's say, two gap phases in your open question versus like gap versus gapless? Is there some nice physical intuition, or it's just
because it's also something you see in physics situations.
Okay, good. Thank you.
And it doesn't follow directly from this.
Okay, cool. I guess because you encoded this looping into the opening the gap, that's why you can't. It doesn't follow directly as a result.
It's sort of to do with the gap properties of the Kitaev Hamiltonian.
Okay.
Because it's it's got a very small gap, so you can't really get the gaplessness, the gapness in that case.
Okay, thank you.
Sorry, I might be a little bit. I was late a little bit. So can you go to the slides where you define the uncomputability for the number?
Where I define Chaitin's constant, or
the word like in the summary you have the you say it's uncomputable. I was curious, what's that definition for that?
Right. Just that there's no algorithm running in finite time, that when I give you h phi, you can tell me what phase it's in.
Like exactly, that's what your definition?
That's more of the definition. Yeah.
Okay, sure.
Can you maybe say a little bit more about these, I guess matrix-valued Hamiltonian elements isn't something that one typically sees in other places, and just some kind of intuition for how one gets that from the Turing machine? So that was the logical progression you build. So is this maybe a family of Hamiltonians, or it's just a single concrete Hamiltonian that comes from a given Turing machine?
It's a
Sorry for the loaded question.
It's a family with respect to the system sizes. So there's a different one for each system size, but we're defining that in a translation invariant way, so it's not really changing that much.
Thanks for the nice talk. In your construction of Hamiltonian, how does the constants look like? Are they astronomical number, or it's a fairly simple general number satisfying certain conditions?
In terms of the local dimension, do you mean?
Local dimension and ABC, let's say.
So ABC are matrices.
Yeah, like you have several parameters in Hamiltonian, in your Hamiltonian, right?
Yeah. So the
Are they like, how, you say it's explicit, how does it look? If you write it down. I'm just asking out of curiosity, if you can.
So I can answer the dimension question.
Yes,
In that
yeah.
it's in the tens of thousands maybe.
Okay, yeah. Okay, yeah. And ABC, it's still like unknown. I'm just asking, but
I'm not really sure I understand the question, but
my question is matrix entries of ABC
Yeah.
are in Z plus Z1 over Z.
Yep.
You do you specify these entries?
yeah, in principle they can be written down.
But it's also as large as dimension.
Yeah, they're d squared by d squared.
Okay, thank you.
Hi, really interesting talk. Could it not be argued that the uncomputability is essentially you want to compute a property of an infinitely large system to infinite precision, and therefore, of course, this takes infinite time? Could we not say that this is essentially what's going on here?
No, because you can do it in some cases, right? So
Then I guess it would be that it's algorithmically random, something along those lines. That there's no shortcut to compute the later digits of the phase transition. Is that kind of the key ingredient that makes it take infinite time?
No, the key ingredient is really that we can embed this sort of universal computation in it.
I see. Thank you.
Wait, actually, I had a question. So maybe that's actually following up on that. It's like we now have like a collection of nice results that show that various problems about like thermodynamic limits are undecidable. Like I was wondering, are there results where we know that these things are decidable? Like say maybe like if the local dimension is below some constant, they become decidable, or is that like a fruitful direction to look at, you think?
Yeah, I think that's an interesting direction. I'm not aware of results where people have proven it for like low local dimension and things like that. I think it is also decidable in the operator algebra framework, which is kind of interesting.
Oh, well, what does that mean? Like, is there still like a notion of like a thermodynamic limit and like number of particle going to infinity?
No, just as in if you like in that framework, you're like working directly in the limit, and then there people have given an algorithm that converges on the expectation of operators in the ground state.
I see. Anyone else?
I can just comment on that. There's a nice result that was a QIP talk, I don't know, 5 years ago by David Gossett, showing that you can phrase the result as like on a 1D chain of qubits, translation invariant, it's frustration free. The result makes everything completely decidable in the thermodynamic limit. So there is probably some threshold, at least for 1D systems, or maybe even for 2D, where for local dimension below something, things might become decidable, and above, I think 10,000 is kind of optimistic. It's probably more like 10 million in our construction. Who knows? No one's actually worked it out in detail. And so, yeah, what this number is really interesting. But the only concrete thing I know of in this sort of setting where you're really doing the physics thermodynamic, you have to finite lattice size and then take the size to infinity rather than working directly in C-star algebras. I think this is the only one I'm still aware of is David's result from years ago. And I forget who the co-authors were. Maybe Seb, were you on that? No. Yeah. But yeah, it's a nice hint that right at the bottom, the maximum number of assumptions you can possibly put to simplify things is there's a decidable case.